This is the problem on the conducting rails, and it reads: the two conducting rails in the drawing are tilted upwards so they each make an angle of 30 degrees with respect to the ground. The vertical magnetic field has a magnitude of 0.050 Tesla. The 0.20 kilogram aluminum rod, length 1.6 meters, slides without friction down the rails at a constant velocity. How much current flows through the bar? Alright, so the aluminum rod has a mass of 0.20 kilograms, that's about half a pound, has a length of 1.6 meters, that's actually 5 feet, so imagine that this one here is 5 feet across, and I guess for conducting rails, if these are railroad rails, then that would be true. They don't say so, it's railroad trails, but I figure I'd mention that anyway. Alright, so I put this here in a side view because I will have to put in some forces, you'll see in a moment, and it's better if we put that in a side view. So here's the rail that slides down the incline, the conducting rails, with a certain velocity here in green that is constant, as it says, and that means that all the forces directing on this rail here as gravity is trying to pull it down are actually canceling each other, because they come out to zero, therefore there is no acceleration, and therefore the velocity is constant. Okay, let's see what kind of forces we have acting on this. Of course, gravity tries to pull it down. Then there's the normal or support force that is always perpendicular to the surface. And then we have to look at what kind of magnetic force is acting on this aluminum bar that is sliding down. So I pulled this picture here from the book. There's too much actually in this picture. I know this is about some kind of magnetohydrodynamic propulsion, but all I really need is this hand here. So the magnetic field is pointing up. The electric current goes to the, I know, kind of like to the left, but into the paper, and that's what I'm pointing at. So it's inside the paper. Of course, here we cannot see it. Over here, the electric current would go this way, positive to negative, that is. Okay, and then the force would be to the right of the electric current, so the force would be this direction. In fact, it would be horizontal. It has to be perpendicular to both the magnetic field that is up here and to the current that goes into the screen, the paper here. And that's again what we see here, and it was the only reason why I took this entire picture out, just to show the hand here that then shows us that the current goes to the right, not to the upper right, but to the right. I'm sorry, the magnetic field goes to the right there. So again, the current is into the paper. The magnetic field itself, we can see it from the other drawing, is straight up, and so the magnetic force has to be perpendicular to both of these, and therefore it has to be strictly to the right. Okay, let me see if I got the angles actually right here on my drawing, and this one here, yep, looks like, how did I turn this earlier a little bit? Huh. My protractor is slightly turned. Why is that? Anyway, it looks like 30 degrees here. My normal force here, by the way, comes out to 120 degrees right from the positive horizontal. That's important when we get to the calculation. So it points to the upper left, so it's 120 degrees from the positive horizontal. Alright, so let's do the calculations. All these forces here have to equal out to zero. If I put them tip to tail, I believe you can see that. I try to do it as accurately as I can. I know it's a little bit off, but overall they should come out to zero, giving me therefore zero net force, zero acceleration, and therefore a constant velocity as it's sliding down. And again, when I write this down, I get this here, the sum of the forces equals zero in this case, zero acceleration, zero net force, constant velocity. Then I split them up into two parts. One of them is an x and the other one is a y. I think I seriously could have written my x a little nicer. There we go. And then I write down the forces in the x direction, which is the magnetic force pointing to the right, plus the normal force, that is the horizontal component of the normal force, which is Fn times cosine of 120 degrees. And I'm trying to do this. I wonder if I ever get my tablet and the pen to do what I want it to do. Equals 0 because there is no acceleration. And then in the vertical I have mass times gravity. Respectively, it's pointing downwards at an angle of 270 degrees, so that would give me sine of 270 is negative. And then I add to that Fn normal force times the sine of 120 degrees, and of course, since there is no magnetic force in the vertical, it doesn't appear here, it would be 0, and of course there is no gravity in the horizontal, it doesn't appear there either, it would be 0. Okay, so I have two equations to do calculations with. And when I look at these equations, I can see that if I get this, all this here to the right hand side, I get all this to the right hand side, then I have the normal force and sine and cosine on the right hand side, and when I divide this by that, well, the Fn is going to divide out, and I will have sine over cosine equals tangent, so that's going to be kind of nice looking. So I'll do exactly that, except for this little piece here where my pen just moved over there. So I'm going to, as I said, these two things to the right hand side, so I'm going to have negative Fn sine 120 degrees. I said a moment ago I divide the sine by the cosine, the y by the x, divide by, again I get this to the right hand side, so I'm going to have negative Fn cosine 120 degrees equals, and then I have this on the left hand side, minus mg divided by the magnetic force. Now the Fn divides out, which is good because they're not asking for what the normal force is. This one here is going to be a number. This one is given in the problem. Of course, we know that acceleration due to gravity is 9.8, and we would get the magnetic force. Well, that's not what they're asking for, but the magnetic force is simply expressed as, more or less simply expressed as the electric current times the length of the rod times the magnetic field times the sine of the angle between the current and the magnetic field. So that's what I'm going to write down. So minus mg divided by the electric current, I, times the length of the rod times the magnetic field times the sine of the angle between the current, which goes into the paper, and the magnetic field, which goes up. Therefore, the angle between those two is 90 degrees, and the sine of 90 degrees is 1. On the right hand side, minus Fn divides out, and sine over cosine is tangent, so I have tangent of 120 degrees. And then I solve for I, and I think I'm just going to write the I here on the right hand side. I equals negative mg divided by LB. The sine 90 degrees is 1 anyway, and then of course divide by tangent 120 degrees. Notice this negative right here, but also notice that the tangent 120 degrees puts us into the second quadrant where the tangent is negative, so this negative here divides out with the negative that the tangent produces, equals all the numbers are given in standard units, so therefore we also have to come up with the standard unit for electric current. And I was about to write that unit on the right hand side, but I might as well write it here. I'm sorry, left hand side. I might as well write it on the proper right hand side of it. So again, all these numbers are given. It's just a matter of plugging them in.